Welcome back, folk. You are back. So you like what we do. So go ahead and like. And then also, I hope you got here because you are subscribing and therefore you were reminded that, hey, we've dropped in another one. We've dropped in another one. We keep dropping them until they can't drop anymore. All right. Anyway, remember to like and subscribe because that's how you're going to be promoting our channel. Now let's go ahead and say last time we are busy with operational amplifiers and we're looking at their configurations, the different ways in which we connect our operational amplifiers. Now we have looked at the voltage follower. We've studied how it is a unit follower. It works similarly to the what to the what call this to the emitter follower in the, if you're working basically using the what, the basic transistor. Now we also said, we did not say, you see, this is why it's important to subscribe, because when we, if we forget to mention some things in a previous session, they might be mentioned in other sections, you know. So right now we forgot to say, where do we use our unit follower, our voltage follower? We use it basically to match to, let's look at this situation. I have a stage 1. I will use a block diagram situation. I have a stage 1. This stage 1 is this output, and I have a problem now. I want to, I don't like the output characteristics. I just like the voltage. I just like the voltage it's providing, but I don't like the other output characteristics of the what, of stage 1. So what do I want to do? I want to protect my next stage, my stage 2. I want to protect my next stage. This stage 1 must supply stage 2, and I want to protect my stage 2. I like the voltage that I'm being given by stage 1, and I want to supply it to stage 2. But I don't like the other characteristics of the output. So what do I want to do? I want to protect. I simply want to provide the voltage through to stage 2, but not necessarily the other characteristics. It may be output impedance, it may be output current, it might be whatever. I don't want those. I just want the voltage. What do? We put a buffer in between. Yes, the voltage follower is also used as a buffer. We put a buffer in between. We call the buffer zone. We put a buffer here in between to say, hey, you are just going to supply what is needed. Supply to the buffer, but the buffer will say, I will only pass what is needed by stage 2. All right. So this here is going to be our buffer. And guess who the buffer is? The buffer is then emitter follower. This is stage 1. This is V from stage 1. Let's call it V1. And it's going to be V in for stage 2. V out for 1. And it's going to give us V in for 2. This is going to be V out for the buffer, but it's going to be V in for 2. So I'll just say V2 in. So this is the input to V2, because all we like is the voltage. All we are going to do is take our voltage follower. So we are going to send the voltage through, but not any other characteristics. So this is working as a buffer. That's precisely what a buffer is. If two guys are fighting in war and you come in as the United Nations and you say, we are going to create a buffer zone here. You guys are not gonna, you are not gonna interact except in acceptable ways. So then you say, okay, you can talk, you can do whatever, but no weapons here. So what are we saying? We can talk. Oh, so talk is our voltage. We are going to supply the talk, not the bullets. Okay, not the bombs. All right. So this is basically the buffering. So our voltage follower can be used as a buffer to protect, what they call this, to also to do what? Remember, what is the characteristic of this guy? It is a very high Z in. So this, and it is a very low Z out. So what does it mean here? It means I am also matching impedances. If I have a stage here that is a very high output impedance, and it's going to feed a stage that is a very low input impedance, I can use my buffer to what? I can use my buffer, my voltage follower, to handshake the two. It's called handshaking. To handshake the two, to make them work together. So this is also, the buffer can also be used as an impedance, for impedance matching. All right, those are the things that we forgot to really mention in the previous stage. I think it was so exciting. We dealt with the gains and how it operates and all that, but we forgot to mention that it is also a buffer. And it is also what? Good for impedance matching. That is what we use it for. Now, anyway, this is not a section on the voltage follower, but it is a section on the next guy. And who's the next guy? It is the inverting amplifier. Let's look at the inverting amplifier. Now, what is that? An inverting amplifier is simply one where the input is sent through the inverting end. So what happens to the non-inverting end? We don't need you, we ground you. But we send our input through remember, except for the comparator, they all have feedback or they are closed loop configurations. Okay, now we send our input through that guy, and our V out obviously goes out through pins. Okay, I'm not gonna say pin 6, 741. It can be pin 6 or pin 10 depending on which one you are using. But then anyway, our output will come out through the other vertex there. Now this is called our input resistance. That is called our feedback resistance. Now how does this work? Now let's suppose V in, V out is there. Let's look at two things here. What is V in? V in is, well, any value. But what is the potential at the other end? The potential at the other end is a 0. Ground is 0. So what happens? This is driven to virtual ground. Remember, we said this guy likens, so he sinks. Because the other one is down to ground, it sinks the other input as well to virtual ground. All right, remember, virtual ground is one concept you will always be asked to, what call this, in most papers, you'll be asked to define that. What is virtual ground? All right, it is when the other input, well, in this case here, the inverting input is sunk to ground simply because where the one input is sunk to ground simply because the other input was grounded, all right, was literally grounded. So it is driven to the same state, it is sunk to the same state, therefore it looks like ground without being ground, without being actual ground. So this is virtual. Virtual is what? It's like a mirage. It looks like you're walking in a desert, there you see water, it's so hot, and you see water there, and you start running, and as you run, the water keeps running away as well, all right, because it is not really water, it is a mirage. So this is also the mirage of ground. It is not really ground, it looks like ground because it operates like ground. All right, let's go and say, because this is like ground, what does it mean? It means that V in is supplied through R in and the other side is ground. So it looks like we have a 1 circuit here where we have V in, and that V in is supplied through R in, and we have ground. What does this mean? It means Ohm's law. We develop a current here, and that current is what? This is R in, by the way. Our current is equal to what? Our I in, we will call it I in, that current there. Our I in, okay? Our I in, oh, okay. Now it's I in, I'm doing in now. It's I in, all right. Our current in develops as a what? Because we have a source and ground. We know it's virtual ground, but because it has the potential of 0, so it is ground. So we have our I in being determined by Ohm's law, V over R, and that is V in over R in. So that is our current. Now this is the interesting part. Our output voltage, what is V out? V out is also wired between, obviously, how do you measure V out? You measure V out between that output thing there, output port there, and ground. But that ground is the same as that, the potential between that and ground is the same as the potential between that and ground, but this is ground, meaning we are measuring across RF. It means our V out is measured across RF. V, R, VRF. Okay, but then now, what do you notice? VRF is going to be, because the input is coming in through the inverting, it's going to be minus. It's going to be a negative value. But another thing that you need to note, that VRF is going to be I in times RF. Why? Why I in times RF? Not really minus, all right, because remember it's going to be an inverted figure, all right. It would have been I in and IF if it was not inverted, but because it's inverted, it's going to be minus I in and IF. Now, why I in and IF? It's because that guy is a massive, we say it should be, by design it should be infinite. It's massive, it's mega ohms. Now, if you have such a value, and it's literally the whole current is rejected, so meaning that I in is rejected and is sent through I what? Through RF. Now, if we send through RF and you have a situation where this is going to be a potential IRF, which is this potential here, that happens to be the potential across RF, which is basically what we said is our output, okay, VRF. So therefore, what does it mean? That means that's our output. What does this tell us? Previously, we said with the voltage follower, our V in and V out were in phase and they were together. But here, look at this. Our V in is positive, our V out is negative. Or we can say VRF, but VRF is negative. It's going to be a negative value. Now we can say, but what is our gain? We spoke of gain. What is our gain? Our gain is equal to what? Now, if I manipulate this, you can see that our V in is very much I in by R in. So what is our gain? Our gain is comparing our V out to our V in, which is basically minus I in times RF over I in times R in. So these two being the same, our gain is basically the ratio of RF over R in. That is our gain. Okay, obviously negative. Why? That simply means inverted. All right, that simply means it's a negative thing, because it's going to give us a what? An inverted polarity. Remember, it's an inverting type. All right, so there is our gain. So what does this mean? It means therefore, ultimately, therefore, since V in, V out is equal to, manipulate this equation here, V out is equal to AV times V in, AV times V in. It means our AV, our voltage gain being minus RF over R in, it will be times V in. That is basically our two formulas to remember, the gain formula and the output voltage formula. I don't think this was, if we didn't understand virtual ground, we would struggle to understand how we get to this point. But if you understand that once one input is grounded, the other is sunk to ground, sinking and sourcing. So to the next stage now, what we're going to do, we're going to deal with the sourcing example. Hope you like this. If you did, there is the like button. Prove that you like it. And then also subscribe, so you know when you drop the next thing. We are going to drop the next thing and you miss out. So till we meet again, hope you had fun. We are having fun. Ciao.